Good morning everyone. My name is Adil KA. Today I'll be presenting on one of the fundamental concepts in computer vision, which are color models, specifically RGB and HSV. Understanding these models is essential because almost all vision tasks rely on accurate color representation. In this presentation, I will explain what color models are, how RGB and HSV work, and why choosing the right model is important in computer vision applications. So my next slide is on understanding color models, the foundation of digital colors. Color models are mathematical ways to represent colors using numbers. They allow computers to store, interpret, and manipulate images. The two most commonly used models are RGB and HSV. Each model represents color differently, and these differences affect how we process image in computer vision task. Color models translate colors into numerical sets, enabling digital processing and manipulation within computer systems. RGB and HSV stands out as two fundamental models in computer vision graphics, each with distinct characteristics. The RGB color model, additive light mixing. The RGB stands for red, green, and blue. It uses additive mixing, meaning colors are created by adding light. Each channel ranges from 0 to 255. For example, red plus green creates yellow. This model is used in LEDs, monitors, and cameras because it aligns with how these devices generate light. Visually, RGB can be conceptualized as a 3D cube with each axis representing the intensity of R, G, or B. This model is ubiquitous in digital displays, cameras, and various hardware due to its direct correlation with how light is emitted. Now I'm going to explain about RGB color cube. This 3D cube represents RGB colors. Each axis corresponds to one primary channel. The origin, that is 0, 0, 0 is black and the far corner is white. All possible RGB colors lie within this cube. Understanding this cube, which is RGB color cube, helps visualize how combinations of red, green, and blue create different colors. The next topic is the HSV color model, human-centric color representation. That is the full form of HSV color model. HSV stands for H stands for hue, S stands for saturation, and V stands for value, which is brightness, offering a more intuitive approach to color. Hue represents the pure color defined as an angle on a color wheel. Saturation describes the purity of the color, ranging from gray to fully vibrant, which is 100%. And value indicates the brightness spanning from black, which is 0%, to full brightness, which is 100%. This model is often used because it matches human thinking. When we describe color, we usually talk about hue and brightness separately. Why HSV is intuitive for humans and useful in vision? So one big advantage of HSV is that it separates color information from brightness. In real world images, lighting often changes. HSV handles this better than RGB. For example, even if a red object is under bright or dim light, its hue remains similar. That makes the HSV very useful in segmentation and tracking tasks. And others are simplified color manipulation. This separation makes it much easier to select, adjust, and filter colors based on human perception, simplifying tasks like color picking and image editing. Another is vision task efficiency. HSV proves highly beneficial in color computer vision for tasks such as color-based segmentation, object detection, and correcting for varying illumination conditions. RGB versus HSV in computer vision. Strengths and weaknesses. RGB is fast and hardware friendly, but it struggles with lighting changes because all three channels are dependent on brightness. HSV solves this by having independent channels, that is, hue and saturation, stay mostly stable even if lighting varies. However, HSV requires converting from RGB, which can add computational overhead. RGB channels are highly interconnected, meaning a change in one often affects the perception of the other. And HSV is superior for a color-based analysis, showing robustness to lighting variations and offering intuitive color filtering. And also, HSV is independent channels. Its channels effectively separate chroma from luminance, enabling independent adjustment. HSV has more enhanced operations, allows operations like histogram equalization on brightness without inadvertently altering the perceived color characteristics. So now we'll see a practical example, that is detecting a colored object. We'll see both the approaches, RGB approach and HSV approach. So in RGB approach, detecting a specific color object using RGB requires defining complex thresholds across all R, G, and B values. This method is highly sensitive to changes in lighting, as altering illumination can drastically shift the RGB values of the desired color. Now we'll see the HSV approach. In contrast to the RGB approach, using HSV simplifies the process significantly. We can filter primarily by the hue range of the target color, largely ignoring variations in brightness. This makes the detection much more robust in diverse real-world lighting conditions. Conversion between RGB and HSV. Cameras capture RGB values, but the computer vision systems often convert them into HSV for easier processing. The conversion uses mathematical formulas that map the RGB cube into the HSV cylinder. After processing, we can convert back to RGB for display. Accuracy during conversion is important to avoid the distortions. The RGB input. The process begins with an RGB triplet, typical for camera captures or display outputs. Formulas applied are mathematical formulas are used to translate these RGB values into corresponding HSV values. HSV output. The result is HSV data ready for color-based computer vision algorithms. So, a conclusion on deciding choosing the right model for your vision task. So to summarize, use RGB when dealing with hardware or when speed is essential. Segmentation or when lighting conditions are inconsistent. Choosing the right color model can greatly improve the performance of computer vision systems. Understanding both RGB and HSV helps us design more robust and human-like visual processing algorithms. So that's all for my presentation. Thank you all.